Okay, cool. Good. All right, I hope everybody sees my screen. And good, yeah, awesome. I hope there's nothing different because I select some advanced options from room that would enable we watch some video clips better, and you could also hear the sound. But I hope from my point of view, you don't see problems. I mean, from the lecture point of view. All right, I don't hear any complaint. That means things are developing fine. We're gonna just get started here. So yesterday we already spoke about brittle fracture. So I mean, first failure, and then we zoom into fracture. And we spent quite some time on brittle fracture, in a very detailed, because brittle fracture was the most decremental kind of type of failure in mankind. Maybe you got really a point of it, and you will see many, let's see, examples, and you also kind of visualize the phenomena in the different scales, you know, from component level to sample level, and finally we bring you to a microscope level. And then you will learn the mechanism. Yeah, so mechanisms basically kind of try to get the three important elements to trigger failure, as we've learned from the movie of Ice Age. So the load, the trigger, and the time, yeah, the critical time or the critical phase to develop a crack to fracture. And then you learn basically the method or discipline, the theory behind it, try to quantify brittle fracture and try to finally predict brittle fracture, right? Now we opened a little bit about ductile fracture. So we spoke about difference between fracture for ductile fracture and also damage. So my drawing is becoming a little bit sharp in a way. Anyway, yeah, so we learned the difference between these two terms, and you've also learned ductile fracture. They have some typical stages, yeah, and I just tried to recall everything here. So usually it starts after necking, and it starts with some so-called void nucleation, and then these voids will grow and to a large scale, and when they grow to a certain level, they will touch each other, and finally this kind of big void will generate some crack propagation, yeah, and then it's fracture. So if we just try to get some analogy with the brittle fracture, you can see all this before is the important part, and this is the final part. Yeah, so this is the crack propagation and fracture part. So we put a lot of effort in brittle fracture trying to understand this, but for ductile fracture, actually I could tell you this is the key. Yeah, because if you remember the stress strain curve for ductile fracture, and this is how it looks like, right? And I can tell you the last part about crack propagation until to fracture is only taking place at the very end of this whole process. So this is something you don't need to care anymore. We only need to know what is happening before that point, because that is the major, let's say, mature life before ductile fracture. Once we reach this point, everything is already too late. Yeah, so this is the difference. That's why for ductile fracture, we care about void nucleation, void growth, and coalescence, especially coalescence, because this is the point things become critical. Yeah. Good. Now let's move to some phenomena. So we will see this is an abstract description of the process. Yeah, and we don't have a video to show you. There was a nice iceberg video to show you about cleavage fracture. For ductile fracture, you don't really see it. So you can only kind of visualize this via a schematic drawing, because everything's happening inside of the material. And what we could show you is some micrographs. So this is what you see after the fracture. Yeah, it's like what you saw for the previous fracture as well with the stainless steels. And here you can see, if you just look from right to the left, so this is a ductile fracture, and you see it typically develops this kind of cup cold structure. So we're looking at a cup part, so the cold part is opposite. And as you can see here, you see this part right in the middle. So these are the part that is making, the major life of the ductile fracture. You see, these are really the developments before this final crack propagation. So at this point, when the crack just propagates in a way, in a rather fast speed, we don't care so much about it. It's still ductile fracture, but this is not the origin. This is not the key point of ductile fracture. So now we look at this and we zoom in, and we zoom in just at one point here to a rather large magnification. So still look at the surface, you see, here you can really find what are the voids I'm talking about. So here you don't see it during experiments, but after fracture you could see. So let's see, this is kind of one void. So you of course just see half of it or a part of it, because the other side is on the other part of the broken specimen. You could recognize there are voids. For example, this is a void. This is a big one. That was a big one. And there's also very small ones. So this is also void. You have to use a little bit of your imagination. This up and down, they're just telling you they're voids. And some very interesting ones. Maybe you see this guy. This is also one void, and this is also another void. You see, just inside of this void, there's something. There's something like, not the material. Yes, you're right. This is the so-called inclusion. You see, they're kind of shiny, and they're not made of, steel. Let's say metal part. Typically, they are ceramic parts. So they're the so-called inclusion, and they're usually very hard. And I could tell you, and this is our acorn for the ductile fracture, because these guys are responsible for the void nucleation, and they're the trigger for a void nucleation. And when this kind of void nucleations are happening, and then you're going to have some, void growth when you continue to develop. Let's just look at the whole picture in a little bit systematic way. So here I'm giving you on the left column this kind of mechanism in a schematic drawing. So when we just pull our sample in the horizontal direction, at a certain point you will generate a lot of voids. So this is the difference. This is already the first, maybe the major difference between brittle fracture and ductile fracture. Brittle fracture, it starts from local. So it starts from, let's say, one point, which is the weakest, or which is the point that is rich, the K1C value, if we use the fracture mechanics to describe it. And that kind of local crack will suddenly become unstable, and that it just goes like that. And then you get your, brittle fracture. But ductile fracture is completely different. So ductile fracture is a kind of populated phenomenon. So it generates a lot of voids in your material body, and at the beginning of the loading already. And then this kind of voids, we're going to interact with each other. That's the second phase. But first, we need to understand why you're generating this voids. Here I'm giving you two examples. So the first one is so-called interstitial free steel. So that means the steel is pretty clean. Not completely clean. It is clean in a way that you don't have many interstitial solid solutions, but you still have what? You still have this kind of inclusions. So this is one inclusion. And I said, they're usually ceramics and they are hard. And compared to your steel matrix. So what would happen if you just, let's say, deform a soft medium, and within a soft medium, you have a hard particle, which is much harder than the soft medium. And maybe you can take a moment to think about what would happen if this is developing. I could already tell you the answer. And because here's soft, yeah, the soft media will be easy to deform, and the hard one is hard, yeah, it doesn't deform that much. So you will kind of develop a inhomogeneous deformation. And that's the point, or that's the reason we would develop some. Look at it here. These are the origin of the voids. So these are two voids already. So if you just continue that, they will become round and they will grow. So they become really a big void. And finally, you will see that from the metallography figure, the void is becoming that big and you have this kind of cute inclusion inside. So this is one very typical behavior for, let's say, clean materials or single phase material. So you don't know the phase very well yet, but I will tell you already next week with a very proper definition. But you can think about for phase, that means the material is behaving rather homogeneously if it's a single phase. On the contrary, we're speaking about a so-called dual phase steel. So here you can see we have something like this color, so green, and something a little bit light, as you can see here, those small islands. The rather lighter ones, they're corresponding to a hard phase. So this one is much harder. They're still kind of steel. They're having very similar chemical composition, having similar crystal structures, but they behave different. So the larger one is much, much harder. So you can imagine they're kind of ceramics. And if you're a little bit familiar with the composites, you could imagine, so this is a soft material, and within the soft material, you're kind of putting some really strong fibers. So you try to enforce the material with strength. And this is typically how you do it in, let's say, metallic materials. And as you can see, we would have a hard phase and a soft phase. When you just deform them, as you can see, everything's deformed horizontally. And you would develop this kind of voids as well, because the mechanism is the same. Yeah, the soft one is already deforming, but the hard one is not. And what will happen? So they will just detach from each other, and then you will develop some kind of voids. So look like this. And this is the beginning. This is the origin of void nucleation. So I hope you get it. So it's basically a deformation incompatibility between a hard and soft phases or components. So this is universal. So I'm just giving you two examples. Actually, this is rather universal for any, let's say, ductile fracture or void nucleation. Yeah. So the difference is the hard and soft, they're always different. Yeah. So you could look at different microstructure features to identify your hard and soft, but the mechanism is always like this. Once you have your voids, so the voids is in your body, and the rest is pretty easy to imagine, right? If you just continuously deform it, those voids are going to grow, so they become bigger, as you see from the left-hand side figure. And from a, let's say, microstructure point of view or microscope point of view, you see these voids are getting bigger and here, and this is even better for dual phase. You see this is really getting larger and larger. This is easy to imagine, but what is interesting is when you really develop large enough voids, what will happen? Yeah, so this is so-called void coalescence. I told you, so some voids are going to meet each other and they develop big one. So how are they going to meet each other? And here's a point, because this process is taking really fast. You don't see it, via certain, let's say, microscope or so, because it's usually happening inside of the material. When we see the fracture, so the material is becoming two parts, it is already too late. That's why there's an interesting study. So these voids are not generated kind of from the material level, and it is actually generated by some artificial procedure. So these are voids or holes milled into our materials. So these are two holes in parallel to each other. So here, the deformation is a little bit different. So here we're applying a load vertically. Yeah, you can see, yeah, for only for this right-hand side figure. So the first case, this kind of voids are gonna develop a kind of ligaments that connect to each other. You can see when we just go with the deformation, the voids are getting bigger, but something is developing between them. You see, this is already something there, and this is another one. And finally, these two are really getting in touch with each other, and it becomes a really big one. And this is so-called void coalescence. And the second phenomena is if these two voids are not exactly kind of in parallel with each other or at the same height level, there's a little bit, let's say, dislocation over there, and you can see they will develop a so-called shear band. Yeah, this shear band will finally get in touch with each other, and you will finally develop a big void as well. If we just try to, again, abstract this phenomena and try to get some, let's say, conclusions out of it. So we would say the void coalescence. So the mechanism for void coalescence is basically driven by these three factors. The first one is so-called secondary pores or secondary voids. You can see here. So the two voids, by the way, these are the acute inclusions. Yeah, you see they are the triggers. When they just grow to a large extent, you will see they develop a ligament to connect each other, but they're not the ligament like a sharp line or so. And actually they're kind of composed of this small voids. So if you just recall the micrographs I showed you before, so we have the big voids, but they're also very many small voids. So these are the so-called secondary voids. They are used to make connections to the big ones. So this is the first mechanism for coalescence, and the second is this kind of shear band. So one or two voids are not so in the same height, they have a certain misalignment, and you will develop this kind of a shear band. So basically, this is just accumulation of dislocations. You could imagine like that way. So if your dislocations like this, yeah, edge dislocation, they just kind of go towards this kind of stress concentration area, and you will develop this kind of shear band, when you have too many dislocations. So meaning that point will become vulnerable, and finally that leads to a failure. So meaning these two voids are going to connect to each other. The third one actually is the easiest one to understand. Yeah, it is so-called coagulation. It is nothing but these two voids are just so close to each other. When they just grow at a certain point, they will just touch each other and become kind of one big void. Yeah. All right. So these are the three void coalescence mechanisms. I think that is already the end for the ductile fracture mechanism. And here we're going to go with some, let's say, quantitative calibration or quantitative description of ductile fracture. So we call it with the theory or modeling. So I have to point out this is rather a kind of seminar thing. Yeah, it's not a full seminar for today. It's basically going to be a seminar for, let's say, 20 minutes or so. Basically, I could show you how we develop ductile fracture and what kind of theory or tools we could use to basically predict ductile fracture, as you remember. So we study the fracture behavior for one reason and one reason only, just to be able to describe it and to be able to predict it so that we can avoid ductile fracture, cleavage fracture in our daily life. And one point before we dive into it, actually different from fracture mechanics. Remember, we learned fracture mechanics yesterday. Yeah, so that was a point. Okay, the pointer is here. And that is a discipline that we could rather use easily or well established to describe cleavage fracture. And for ductile fracture, we're using so-called damage mechanics. So this is another discipline which is just populated in the last few, let's say, decades, basically to describe ductile fracture and to predict ductile fracture. And I have to tell you, this is still a very much ongoing research field, because you can see ductile fracture is much more complicated. Yeah, so we have those voids, they just develop, at kind kind of random places, and you want to describe it and you want to try to quantify it. So it's much more difficult than a cleavage fracture. That's why you will see a lot of approaches going on, and we finally try to get the one that works the best. All right, so this is a kind of category. We describe what are the damage or fracture damage mechanics models. And you know we have brittle fracture, but we're going to focus on the ductile fracture. So basically we have those 4 approaches or 4 categories of models to describe, let's say, ductile fracture. I will not stop here for too long. Let's just go to the phenomena. So here I'm telling you some driving force for the ductile fracture. You know, we know the mechanism is that there are lots of voids, and these voids are kind of growing and they coalescing, and finally they develop a very big void that leads to fracture. How do you describe this? Via mathematics, via equations, because you can understand mechanism just by words to describe it. That is a qualitative description. If we want to do some prediction, we have to use some quantitative description. Yeah. So you have to put everything into equations and try to measure it. Yeah. So you probably could imagine, okay, we have voids, maybe we can count the number of voids. Maybe you want the voids becoming too many, becoming too critical, and then they will connect to each other, and then we have the final fracture. So that's one way. So we will talk about that way even in a little bit later. But there's one simpler way that is discovered by, let's say, Professor Lemitron, and he also created one kind of discipline or one kind of category for the ductile fracture damage mechanics models. And that is what he found. When you just do a tensile test, when the ductile fracture is developing, so when you have many voids generating, we see there's a degradation of the material. So we define the damage as a irreversible degradation of the material. And this degradation is reflected to the stiffness. Yeah, so the Young's modulus. Basically, when you do a test and you load and unload and you load again, you will see the stiffness, the Young's modulus is getting smaller and smaller. Yeah, you probably could imagine, right? When you have too many voids becoming in your materials, your material is becoming porous, it is becoming less strong, right? And that is why the Young's modulus is degrading. And then he basically formulated, so the actual Young's modulus, right, divided by the initial Young's modulus. Sorry, that was bad writing. And this is the kind of remaining strength, and you use 1 minus that, and this is the kind of loss, and he defined this as damage. So this is so-called D. And then he made a plot, the D over local strain. You see, we find such a pattern. So the pattern is at a certain stage at the beginning, you don't have degradation of your Young's modulus, so you don't develop damage. This is completely kind of in line with our mechanism. Yeah. And at a certain point, usually this is related to somewhat necking. Yeah, and the damage starts to develop, and it goes even in a linear pattern. So that was interesting. It goes kind of in a linear pattern. And recently, because we have more, let's say, advanced equipment, this is a study by the X-ray microtomography. We also call it micro CT. Maybe you know when you go to the hospital, you quite try to visualize something inside of your body, and you're using this. Exactly, we're using that the same thing in a test. So this is what we did with a virgin material. So here you can see, you don't see too much things. You see some black points. So these black points are usually referring to some voids or inclusions or so. But generally speaking, the material is pretty clean. When you just deform it, you can see this is the last frame of this micro CT pictures before the final fracture. You see there are lots of voids developing, especially at the necking area. So you see each black point is kind of corresponding one void. And then the scientists over here made some quantitative analysis. You see this is kind of a number of the voids per volume. Yeah. And here's local strain again. And what they found is, you see, at the beginning, you don't have too many voids, but at a certain stage, the voids start to grow, or the void numbers start to grow, and you're becoming really a lot. And this is also going with different geometries, but we're not going to talk too much about that. The second feature. What you should remember is the void really develops in such a pattern. And then this is some work I even personally did just about 7-8 years ago. And we kind of inspired by this experimental finding. And then we formulated theory and formulate the equations to describe the ductile fracture. To be honest, the ductile fracture is a discipline that I started my research on about 10 years ago. And we're still doing it. And we're still trying to solve many, many problems at the moment. But this is a beginning point that we contribute to this discipline. And it's something really solve many engineering problems. I could give you very simple, let's say, conceptual idea about this kind of modeling approach. You remember we have our material, let's say this is the true stress strain curve. This is the ideal case if your material is just deforming without any problem. But we know, yeah, there's gonna be voids generating, there's defects in your materials, and that's gonna generate the voids. And from those experiments, you see, we will have the so-called damage invisible at a certain point. And after that point, the damage is going to develop. The voids are going to develop in linear pattern with respect to the development of your local strain. Yeah, so these are two phenomena. What's important is you describe these two in mathematical language and you connect them with each other. So what does the damage do to your material? So it does two things. The first thing is it makes your material softer. Yeah, you see, this is the ideal case. When the damage is developing, before nothing happens, only when the damage is developing, you see your material starts to be weakened. This is the real stress strain curve. When your stress is becoming zero, so meaning what? Your material is kind of fractured, right? So this is the first thing I kind of show from this figure. And the second I didn't show is what Professor Lemaitre discovered. The damage is also weakening your Young's modulus, weakening your stiffness. And that is a 1 minus d to your Young's modulus as well. So that's the second point. So it's pretty simple, right? You got the point for a ductile fracture model. And these are some, let's say, advanced features already, just to show you we could do the model in a different, let's say, categories of phenomena. And these are the equations. So you can see not too many, around about 20 equations or so, or 20 key equations to describe this ductile fracture behavior during the deformation. I remember last year, I asked some of you here, did you, for example, learn this equation? This equation actually pretty simple. It's so-called the elastoplastic strain split. And this is something we learned already from this course. When we have, strain imposed to a material, we're going to have stress. That is something you remember. So this is the point. Let's say your total strain is like this. But, when you just unload, your material is going to go, that was bad. Your material is going to go like this, because the remaining is so-called plastic strain. And the recovered part is so-called elastic strain, right? So that's why we have this equation. The total strain is equal to elastic pi plus the plastic strain. Yeah, I think this is just a starting point. And the second equation is the kind of Hooke's law. What we add is this 1 minus d part, meaning your kind of stiffness is getting is getting degraded by the damage. All right, I'm not going to show you all the equations later. If you're interested in it, yeah, definitely you're welcome to come to our lab and to make some personal contact over there, and we will try to show you some interesting studies over there. Maybe you can find something to do. What is important is I show you a case study that I showed you at the beginning of our course, what this kind of models, or to be more specific, what our models could really do. So we developed those equations to do what? Yeah, so I already told you, basically we want to use those models, those theories to predict ductile fracture. Yeah, and we could use it to predict, let's say, some tests. You see, this is a little bit more advanced tests than tensile tests, because we're generating some different features in the material. Yeah, and more importantly, we should use that to predict some component. So this is a so-called crash box. Yeah, you know, this is a part of in your crash system in a car. Every car has this guy. So usually you have two of this. So they're just kind of put there to be able to absorb energy when you have a crash. So the passengers inside the cabin could be protected. Yeah. The way for this kind of structure to absorb energy is to generate this kind of folds. Yeah, initially it is a completely column. You will see some nice video over there. And what people worry about when they just make this structure in the car is they don't want this kind of component develop fractures. So we just want it to deform in such a way, but we don't want, for example, if you develop a fracture at this point and this component is becoming completely two parts, and then it lost its function. So it cannot protect you from a crash by absorbing energy. That's why we should have a model to be able to predict it and to basically tell the designers or material engineers, if you choose this material, if you choose this geometry with this thickness, your car will be okay. So the passengers are safe. But if you go with a thinner thickness or so, okay, that's not okay, yeah, because you're gonna develop fracture over there and you shouldn't use that. So this is the purpose of it. Good, and here is some, let's say, fracture parameter calibration. So this is done by some lab scale tests. You can see from these tests, we can predict already the so-called force and displacement curve. You know, the pink one is basically experimental data, and the dashed black one is the model prediction. You see, the model is predicting quite well about the force displacement curve. So this is one geometry, this one, and this is the second geometry. Yeah, both of these two predictions are pretty good. And this is the component level. This is a crash box prediction. You can see this is the video here. The left-hand side experiments, real time. So this is a kind of a hammer dropping from about 10-meter height. And this is kind of mimicking a crash with around about 50 km/h. You know, typical urban speed when you just have a crash with this kind of speed, and what would happen. So this is the physical experiment. So I have to tell you, it's an expensive one, and it's not one that you could reach like daily. Yeah, otherwise, you know, we'd better just do experiments. You know, we try different geometries, we try different thicknesses of the material, and so on. But even that, you would have tons of experiments to do. That's why we're going to use the models, basically try to optimize the geometry and so on. Actually, for those guys just 1 year older than you, so they just came to this course last year, and now they're doing a project course, and one of the groups is trying to do a simulation like this exactly, and to try to optimize the geometry of this crash box. Maybe it can absorb better energy, or maybe it can be thinner. So by thinner, automatically you're making your material, you're making your weight of the car lighter, and that is, you know, making a large impact at the moment to the environment, to the sustainability, and so on. Okay, good. So after the video, actually, you could see we can also check the force displacement curve again, and where's the crack compared with the experiments. So that, yeah, these are some detailed checking for different places. So this is something we will not talk about at the moment. So this is a study actually completed by Ms. Venchiliu, yeah, about 2 years ago, and it is published on the International Journal of Mechanical Sciences. So if you're interested, try to Google it, you will see all the details. Furthermore, if you're interested in the topic and to do all this FEM simulation, you will also be able to get a touch about it during this exercise this week. So try to be there. And you see, that was a complicated model. So you cannot do it personally, I would say, because you basically we need derived equations, and those equations are written in a computational language by Fortran, and you can run it as a subroutine with Abacus. So you need some, let's say, training and knowledge over there. But of course, if you're interested in it, don't hesitate to contact us, and we will find something for you to play with. But during your exercise, we will show you a rather simpler model. So this is so-called GTN model. And the GTN model is the second important category of the ductile fracture modeling. And this is relying on the kind of quantity or the idea to measure the ductile fracture via the voids. So the main concept here is so-called void volume fraction. So they're exactly using this kind of the number of void or the volume of voids to be a measure of damage. This is very direct. Yeah, you can imagine this ductile fracture mechanism over there. So this is the void volume fraction. The point is, one is void volume fraction is reaching a critical value. So it's a little bit like the K1C, right? If that value is reached, you try to find what is your critical value of your material. And once it's reached, you will trigger the ductile fracture. Yeah. The key equation in that model is how the void volume fraction is gonna becoming larger, right? We're having more and more voids, and the existing voids are getting bigger and bigger. So that's why the evolution of the voids, so this equation is the second important one, is kind of decomposited into two. So it is first driven by the growth of existing voids, and then it is also driven by the new voids. So the new void nucleation is also contributing, let's say, the water volume fraction. So these are the two important equations, and you have also, let's see, this equation you see before, and this is degradation. And this is the yield criterion. I will not tell you about that because this is beyond your current knowledge. But these two important ones, you got the point. So they're completely inspired by the mechanism. And within the model, you could see this equation over there. We have a few, let's say, so-called parameters to calibrate. So how to imagine this? Actually, this is easy. If you just imagine any model or any law you have learned, there are always some so-called material parameters or fitting parameters. For example, you know, let's say the gravity law from Mr. Newton, and we have the mass, we have the force, and so on. But there's always this G, right? This G parameter. So of course we could measure it, yeah, and it's a constant. It's a universal constant, more or less. That was rather easy. But in our model here, because it's describing a local phenomena and it's material dependent, so these parameters are nothing but G, but you need to calibrate that individually. So it's material specific. And what they will do is, if you just look at this diagram here, so here is the stress rate curve without damage, so pure elastoplastic. And when you have the voids, when you have damage, you can see we will kind of construct such a behavior. And by just choosing different Q parameters, you basically would, realize something like this. So it breaks sooner or later with more displacement or less, something like this. And you will be able to plane this model. So with in exercise a little bit. And this is also the second part about this volume fraction, how it will grow, and that leads to the final fracture. And that's the table. So we will not show you how the parameters are calibrated. So this is the table containing all the calibrating parameters. You can all imagine them as a G, right? It's a material constant. If you do a research in this field for a ductile fracture prediction project, one of your most important tasks is basically to calibrate those parameters. Yeah, but in the moment, we don't need you to do that. So you imagine these are the G's somebody has already completed for you. You will basically use it and try to make some prediction. So in the exercise this Thursday, you'll be able to run a GTN damage model and feel the success of predicting a failure by using FEM, so finite element method. If you haven't learned it, that's good. Now you finally know how that could be correlated with some, let's say, experiment at the moment, but you can imagine that experiment as a crash box, as a huge component you're designing. Yeah. And if you haven't learned FEM before, that's also fine, because you will learn really basically starting from scratch. A very nice exercise for you to go through. I'm sure you will be kind of thankful for this kind of exercise, because you will be able to run many problems with what you learned with FEM. All right, so that was about ductile fracture. So we spend a little bit more time on a, let's say, quantification about ductile fracture and how we could use models, mathematics, to predict ductile fracture. And now I think we are done with brittle and ductile fracture. And now we'll open a something in between. So we are not going to other failures like fatigue or creep. We're still at fracture. And I just want to ask you one question. We have brittle and ductile fracture. We also have the definition about brittle and ductile materials. Yeah, so maybe you remember steel. Let me go to the next slide. Yeah, steel is a so-called ductile material, right? Remember that. And the ceramics are typically called brittle materials, cleavage materials. And why we would have so many catastrophe, so many important fracture of steels. So you can see the Titanic, and on the second hand, you would see this Liberty ships, and here the fracture is kind of more, let's say, significant. You see there's a big cleavage fracture over there. And why would this ductile steels could develop brittle fracture? I would give this chance to ask some of you. Maybe you could give me some answer. Alexandro, are you there? Can you give me some idea about it?
Can you repeat the question, Professor?
Yeah, my question is, we usually consider metals are so-called ductile materials, for example, steels. And why would could steel develop so-called brittle fracture? Do you have any experience with it or any thought about it?
Because it has also a temperature dependence. Depending.
All right, that's good. That's good. That's a very nice answer. You are already touching one of the features. So I would also thank you, Alexandra. Let me also ask somebody else. What about Atina? Atina Nimic?
Oh, Etienne. Yes.
Oh, Etienne, sorry.
No other. Maybe is it as well due to some process like hardening or some treatment on the alloys?
That's an interesting perspective. So you're taking the process into account. Very nice. Good. Let me ask so thank you, Etienne. And what about, oh, there was one I was looking at, but now it disappeared. What about you, Robin Lilymans? So Robin, are you with us? If you're speaking, please unmute yourself. There's also one called iPad. So remember to correct your name when you come here. Try to use your full name. All right, I think that was some already very good answers given by Etienne and also Alexandro. So now we're gonna move to the point that I tried to give you an answer. So you know the brittle fracture could still happen even to ductile materials. There are three kind of conditions to allow this happening. So the first one is so-called very high strain rate. And the second is deformation at low temperatures. And that was one point Alexandra mentioned. And the third one is about the presence of a notch. Actually, if you just try to take something common from these three phenomena, this three phenomena is basically improving your material's strength. You see, when you have high strain rate, the strength of your deformation will be higher. When it's low temperature, the strength will be also higher. And this one is a little bit harder for you to imagine, but it is basically also doing the same. It is improving the strength of your material. And by improving the strength of the material, you will improve, the principal, the maximum principal stress that is really contributing to the cleavage fracture. And the whole material is kind of becoming very close to that threshold, which is finally reflected as the K1C. And you could also think about there's a threshold strength, local strength. And if that strength is reached, meaning your material will go to cleavage fracture, no matter it is a ductile materials or brittle materials. So that is the underlying mechanism why for ductile materials, we could still have, let's say, brittle fracture. And we have a specific test basically to kind of enhance these three features. So either get a high strain rate or try to get a notch, or you can even deform it at low temperature. This test is so-called Charpy toughness test. It is invented by a French engineer, so-called Mr. Charpy. And the test itself runs very simple. So here you put your sample at a lower position, and then you go with a hammer. So the hammer just will rush from a certain height with fast speed and breaks the sample and it goes to a final height. You see, we will have some energy to drop the hammer when it goes off. And when it goes to another level, so this is the energy basically remaining. There's the energy has to go to balance. So what is the difference? Is the difference basically assumed or consumed by the sample. I have a nice video here basically to show you how this runs. Let me just try to get off my pen and run this video for you. I hope you're gonna hear the sound.
The Charpy.
Do you hear it? Can someone confirm?
Yes.
Yes, we hear it. Yeah.
Awesome. Well, let's go on.
Impact test. The standardized Charpy impact test has been designed to measure the toughness of materials under impact loading and multi-axial stress state. A pendulum impact testing machine is used
Sorry.
to do so. The pendulum on the machine has a heavy weight at the end. This is lifted into the starting position in step 1. Then the tester checks whether the testing machine has been adjusted accurately. In order to do this, he turns the drag indicator downwards and releases the pendulum without a test specimen. The drag indicator stops at position 0. This proves that the pendulum has the correct starting position and that the friction is correctly compensated. The machine is ready for the tests. First test, strain-aged plain carbon steel S235. This is our test specimen. It has been machined to standardise size and shape with the characteristic V-shaped notch. The tester places the specimen on a support in the lower part of the machine and adjusts its position with a centering device. Next, he turns the drag indicator downwards again and checks that everything is prepared correctly. Perfect. The test can begin. The pendulum is released, it swings downwards and hits the specimen with its rounded hammer peen. The specimen absorbs part of the pendulum's energy, so the pendulum doesn't reach the full height on the other side. The amount of energy that has been absorbed by the specimen can now be read off at the position of the drag indicator. It only amounts to 13 joules in this test. Here is the main principle of the measurement. In its starting position, the pendulum only has potential energy. It is given by mass of the hammer m times gravitational acceleration g times starting height capital H. After the pendulum has been released, the hammer moves downwards, hits the specimen and then only swings to height small h. Exactly at the first reversal point, the pendulum again only has potential energy, which is m times g times small h. The energy that has been absorbed by the specimen is called notch impact energy, kV. It corresponds to the difference between the two potential energies. The first specimen only shows very little plastic deformation. A mostly flat, slightly glittering fracture surface has been formed. This is another important indication that this kind of steel is only able to absorb small amounts of notch impact energy. It shows mainly brittle behaviour due to the strain aging effect. Second test. The second specimen has been made from normalised steel S235. It is also placed on the support and centred. The tester turns the drag indicator to its starting position, rechecks all safety measures and releases the pendulum. This time the impact sounds much deeper and richer. An impressive energy of 182 joules has been absorbed by the specimen. Here the specimen did not break into two pieces. Instead it was pushed through the counter bearings under heavy plastic deformation. In comparison with the strain-aged steel, the normalised steel absorbs much more notch impact energy and behaves in a very tough manner.
All right, I think we can stop right there. And I also realize it's a time for us to take a break. And so we will continue our lecture at 11:15 again. So everybody take a small break and see you later. Small freshman for the lecture. And now we know the Charger test, how it works. And you also know let's say ductile materials could also kind of experience some brittle fracture due to those three possible elements. And here I'm giving you a little bit more underlying mechanism. So we explain it from the equation point of view from the K1C value from the local critical, let's say, maximum principal stress. But you probably is wondering still why that could happen, but why some other materials do not happen. So this is one, let's say, a explanation about it. Just 1 second. Let me find my pen back. Okay. So actually, for not all the metals would have this so-called ductile to brittle transition. Yeah, and it usually happens to our BCC metals. So these ones. So they typically will go. So here you see this is temperature. And on the left-hand side is so-called impact energy. By the way, this kind of energy is also called kind of toughness. So it's usually called Charpy toughness. Yeah, so the KV value is typically also called toughness. As you can see, there are many toughnesses. Yeah, so you have to really distinguish when you join a conversation, when you engage in kind of discussion. When people are talking about toughness, always be clear what kind of toughness we're discussing about. And you see, for the BCC materials, they would go with this so-called ductile to brittle transition, and this is how it looks like. Yeah. So when the temperature is very low, so the video showed you two different materials, but actually you could also imagine that goes with two different temperatures. So for room temperature, you have high toughness, and for low temperature, you have this kind of low toughness, which is correlated to brittle fracture. And for FCC or HCP materials, they don't typically experience this kind of ductile to brittle transition, at least not to a usual low temperature. Of course, if you go extremely low, and that could still happen, but for a usually low temperature, the brittle would not take place. Yeah, actually the reason is very much connected to the structure. Yeah, maybe you could already imagine, but I will give you the answer. You know, for FCC SCP, you still remember, they have their slip plane. The slip system is on the 111 plane, right? That is a most dense packed plane. Your atoms are really just touching each other. So that makes the dislocations kind of easily moving. So the mobility is much better, especially when it goes to low temperature. You really need a high energy to activate your dislocations to move. Yeah, when your atoms are close packed, when the slip plane is on the close packing plane, yeah, that is somewhat easier. But remember, for the BCC guys, yeah, their slipping plane is not on the most dense packed plane. It is not 111, but it's 110 or 112 or so. So the atoms are always a little bit distancing from each other. And that little difference makes the dislocations really hard to move. So this kind of actual hardness brought by this distance requires a lot of more energy to activate dislocations to move, especially in low temperatures. And that energy is, for most of the time, higher than the energy your material could kind of withdraw. And then you will basically first trigger fracture, then moving the dislocations. So that is why for the BCC materials, they would typically experience this so-called ductile brittle transition. Yeah, I hope you got it. And that is a good refreshment for you to remember what you have learned just last week or even 2 weeks ago. All right, I think with that, we can finally close our session on fracture. And you learned brittle fracture, ductile fracture, and also, yeah, for some materials, these two fracture modes could be just switched between each other. And now we're gonna enter the third type of failure, which is so-called fatigue. And I will begin actually with a video. Oops, what happened here? Because you don't have the chance to see the test. But here I basically try to show you how the test looks like. Let's go with it.
Fatigue test. Many everyday items are not loaded uniformly, but rather non-uniformly with periodically changing loads. This is quite obvious in off-road biking. Frames, handlebars and wheels are subjected to high alternating mechanical loads. It is just as obvious in the case of a garage door spring. The spring is unloaded when opening the door and loaded when closing the door. The connection rods of this old compressor have endured a large number of rapidly changing tensile and compressive forces. Even when cycling quite moderately in the city, many components are exposed to periodically varying loads without us being aware of it. The crank arms are alternately under load, then swing back almost load-free, are under load again with the rhythm of pedaling. The spokes, the pedals, even the individual links in the chain are stressed periodically. Also, the railway bridge over the River Rhine, seemingly totally addressed, alternately has to bear the additional burden of a heavy freight train and then only its own mass. Aircraft experience quite different stresses during take-off and in turbulence than on ground. This type of loading is generally termed fatigue loading, and the material responds to it, fatigue. The term fatigue is used because it takes some time for the failure to occur under repeated loads. The problem with materials is that they normally endure less at repeated loading than with a once-only load. The wire does not break when first bent, but bending it back and forth repeatedly leads to an early fracture. This bicycle crank arm had only been able to endure the cyclic loading for a certain time before it broke. The fate of the garage door spring was the same. It had borne the opening and closing of the garage door about 60,000 times before it finally fractured. The broken exercise equipment, a torn blade of a fan, a bandsaw blade full of cracks, the broken screw, a defective universal joint, and many other examples show how important this phenomenon is. Each day, thousands of items break due to cyclic, often repeated loading. How can we make sure that all these components withstand the cyclic loads? To achieve this, one has to test the materials appropriately. We intend to measure the fatigue strength of a frequently used steel in our laboratory. Hot-rolled steel rods made from the structural steel S235JR are used as base material. In order to eliminate the influence of the surface and to stress the material in a well-defined manner, suitable specimens have to be machined from the rods. This specimen type would be ideal. The shoulder-shaped ends have been designed for safe gripping. The actually tested region is cylindrical with a diameter of 6 millimeters. The material tester goes to the workshop to get 10 specimens manufactured from the rods, not just one. All of the specimens are as identical as possible. Back in the lab, he has all specimens ready for use and picks out the first one. He mounts the specimen carefully and securely into the fatigue testing machine. Together with two half shells, he inserts one end of the specimen into the right specimen grip. With a union nut, he locks the right end of the specimen. Likewise, he mounts the left end of the specimen into the left specimen grip and tightens the nuts. The preparation is now complete. The material tester then selects the appropriate test parameters on the control computer. He intends to load the first specimen alternately with a tensile force of 7 kilonewtons and a compressive force of 7 kilonewtons. The mean force is 0. A click on the start button and the testing machine begins to stress the specimen periodically. Our fatigue testing machine is equipped with a mechanical resonance drive. The specimen is connected at its left grip via a load cell to the machine frame. At the right grip, a spring is mounted and there in turn a mass. An imbalance stimulates the mass to vibrate. Longitudinal guides prevent the mass from vibrating in the transverse direction. Via the spring, the test force acts on the specimen. By varying the excitation frequency of the imbalance, the test force can be controlled. In our case, the specimen is loaded with about 25 cycles per second. Meanwhile, the first specimen has already endured over 300,000 load cycles and still seems to be intact. In reality, however, several cracks have already developed starting from the surface, the so-called fatigue cracks. With each load cycle, they grow a bit further into the specimen. The biggest crack gains the upper hand, grows the fastest, and finally leads to fracture after 381,000 load cycles. The first test is finished. The material tester removes the fragments cautiously and inspects the fracture surfaces. At first glance, the fracture surface looks unimpressive. A closer look reveals two regions: the rather dull, predominantly flat fatigue crack propagation area and the rough residual fracture area. The residual fracture area results from the final catastrophic rupture. The fatigue crack propagation area has developed during the cyclic growth of the fatigue cracks starting at the surface of the specimen. What does the fatigue crack propagation area look like at higher magnification? One of the fragments is carefully placed on the specimen stage of our scanning electron microscope. Now we can investigate the fatigue crack propagation area in detail. In some places, but not everywhere, parallel grooves and ridges can be seen, the so-called fatigue striations. Each groove and each ridge has been formed by an individual load cycle, a typical phenomenon. Of course, now we want to know how many load cycles this material can endure with other loads. For this purpose, the material tester picks the next specimen.
All right, I think we're gonna stop there. So if you're interested in what happened to the second specimen, you could watch the video on your own. You know, the link is here. You can just download the material from my courses. So by the way, the pre-version of the slide is already uploaded to my courses. The final one will be done after today's lecture. All right, so I think now we can move on to
The higher alternating load for the second.
To the actual course material I prepared for you. And that was not only the test, actually the video also gave you a very good, let's say, background or motivation about fatigue. Yeah, this third type, or let's say the second major type of failure besides fracture. And differently from what you have learned for fracture, you see we spend most of our time on fracture, because that is the important fracture, or not most often see, but that is a very important failure type in our daily life, not just for service, but also for producing stuff, for manufacturing. Yeah, fatigue is something more related to service, only for service. But for fatigue, we're gonna use a different learning pace. So for fracture, you learn, different phenomena from large scale to small, and you learn the mechanism in deep, yeah, and you also learn basically the way how we could quantify, predict the theories, the methods, and the models. For fatigue, creep, and corrosion, so these three guys, we're gonna learn in a rather, let's say, shallow way. So you will learn what is the definition about fatigue and how we kind of measure it from experiments. How do we describe it a little bit? This phenomena, something similar to the stress strain curve, but we will not dive into the mechanism. We will not dive into the theories to predict it and so on. So this will be more related to advanced course. So now you know how we're gonna learn it and what I'm requiring you to get the level. So maybe this helps you to kind of orientate yourself with the depth of this learning. Now, back to fatigue. So fatigue is what the definition goes like: failure under lengthy period of repeated strength or strain cycling. So that is the formal definition of it. Now you already feel what is about. First of all, this fatigue is taking a kind of time period to happen, but this is not necessarily true in terms of time. It is more in terms of cycles. So the tester didn't show you, actually the fatigue loads goes like this. So we have time. So this is time. And you see there's a repeat stress or strain cycling. So let's say we go with the stress. Basically, you will have kind of, let's say, tensile stress. The tester gave 7 kilonewton. Yeah, that is a force, but you can reflect that into a stress. And it goes with the plus 7 kilonewton, and then it decreases and it goes negative 7 kilonewton, and it repeats this cycle again. And just like this, yeah. So this part is called one cycle. I hope you recognize this is called one cycle, and then the second cycle, and so on. So this is so-called repeated testing load. So fatigue usually undergoes millions, kind of, or even tens of millions, hundreds of millions, kind of this cycles, yeah, for you to get the fracture. But if it's taking a lot of time or not, it depends actually on, maybe you can imagine already, yeah. It depends on the cycling frequency. Yeah, if your frequency is as big as that video, about 25 hertz, so basically you are repeating your cycles 25 times per second, then, you know, million will take kind of days. But if you're having 20K hertz, yeah, that will just take hours to get your final fatigue. Or if you take 1,000, tens of thousands hertz, yeah, that will take just minutes to get it failure. So the period of time is not necessarily true, but a large number of cycles is the truth. Yeah. So this is about fatigue, and we know already about the cycle frequency, or the kind of one of the most important parameters for these tests. And then the second two is, first of all, the strength. So that is the strength that you're going to apply to it. So if you go with the completely symmetric, so negative, so plus and negative, both same stress magnitude, and then you're going to arrive at a zero mean strength, right? It's basically the average of it, but you don't necessarily need to go always symmetric. You could go, let's say, 7 kilonewton plus and 4 kilonewton negative, and that will give you a different mean strength. So the mean strength will make an impact. I will just show you in the next slide. So these are the three important parameters for the fatigue test. Of course, this is stress driven. If you go strain driven, this will be the strain, and that will be the mean strain. You know, it's basically everything's the same. What's important about fatigue is usually we study fatigue within the elastic region. So what does that mean? That means the maximum strength that you apply, so the sigma mx, either negative or plus, you typically control that below your yield strength. Yeah. So fatigue is a failure typically happening within the elastic region. So you don't deform elastically like the guy showed with this spring. If you just deform it once, your material is completely fine. It will go back to, you know, the original place. Yeah, but you just deform it millions of times. Even though you don't reach any plasticity, your material will fail. And this is caused by fatigue. And this is stress. But if you go with the strain control, that means your strain is typically under 0.2%, you know, the proof strain that we talk about for yielding. The second point to remember is fatigue actually is the killer for many engineering materials or structures, because that is the cause for 90% of failures for engineering structures. Yeah, so you probably will see finally it's a fracture, but as I told you before, fracture is the final exhibition of a failure. So the root is about fatigue. Yeah, and that's basically what I would like to tell you about fatigue as a definition. And then we try to find a figure to describe it. You can imagine this as our stress strain curve for tensile test to fail or so. So for fatigue, we're basically describing a so-called fatigue life. This is so-called cycle to failure. And this is the end. I'm already telling you in the previous slide. But you should imagine this N is always associated with a stress amplitude. So if you apply a high strength, yeah, your N is going to be shorter. Yeah, so if you apply a stress very close to the yield strength, so let's say we go with this stress, and then you start your cycle like this, right? I can only draw a few, maybe only one, but you can imagine in the real time, you're going to have something like tens of thousands cycles, and boom, your material got filled, and then you see, okay, I get 1 point. For this kind of stress amplitude, my fatigue life is tens of thousands. And then you go to a smaller fatigue life, and you go smaller stress amplitude, you repeat your tests, and you record the fatigue life when your material got failure, and so on. Typically for BCC materials, you will have such a phenomenon. So when your strength is below a certain threshold, and this threshold has got lots of names. So one is here written, fatigue limit. It is also called fatigue endurance, endurance limit, and endurance strength, and many terms, but basically it's telling the same thing. So when your applied strength is below this threshold, you kind of get a permanent life. So your material will not get a failure to a large number of cycles. Maybe you wonder, wow, that's a miracle, right? But actually this is also not true. Because recent studies already is developing. Actually, this is part of your room phase studies. Back to your master program, right? Because they can perform very high cycle fatigue, something with the 20K or 50K hertz for a test. Then you could reach this kind of billion cycles, because for 25 hertz, it takes probably months or years to reach this kind of cycles. That's why people think, okay, that is going to last forever. Nothing lasts forever. That's why when you just have so much frequency, you will discover actually this still happens. So your fatigue still happens. Yeah, and that's something extra to tell you. And this is another kind of study, basically from aluminum, let's say, and it doesn't show this kind of endurance strength. It just goes on and on. So this is a very important figure for you to remember about fatigue. I think that's basically what it is. And something extra that I would like to tell you is how do we, because we don't have a model, basically, that's the part how we study fatigue and creep and corrosion. But what I would tell you is how do we avoid, how do we improve fatigue life? From experience, from some, let's say, qualitative measures. So the first thing to do it is reducing the magnitude of the mean strength. This is something for you to just understand. The mean strength tells you kind of how much tensile strength you're going to impose to your material. Crack can only develop at tensile loading. You kind of open your material, right? Either voids or micro cracks. You have tensile loading to open it. If it's compressive, you basically close your either crack or voids. So compressive load is basically friendly. Tensile load is the dangerous part. That's why if we just kind of increase the mean strength, if it's becoming smaller in terms of tensile, or this is here, or it's even becoming inactive, you basically improve your fatigue life. And the second way to improve your fatigue life is closely correlated to that, is to introduce some surface treatment by adding a compressive stresses. This is what you could see from the video as well. You see the fatigue crack goes from the surface. And if you just kind of impose some compressive stress on your surface, the first way is by shot pinning, basically using some short particles to impact your surface to create this kind of surfaces. And due to this kind of creation, you're giving a compressive stress on your material. And the second way is to do this so-called carburizing. Yeah, you will learn this. And remember, there's carbon rising. Basically, you use a carbon-rich gas to let the carbon atoms to diffuse into your surface. So this is a gradient structure. You have lots of carbon atoms here, and then more and more it vanishes because it cannot diffuse forever. And due to this carbon atoms, you know, they're going to stay at a certain place interstitially or substitially into your materials. And that kind of crowded situation will create also a compressive stresses on the surface. We'll talk about this in probably 2 weeks or so, because this is one of the processes to do. And the key is to prevent fatigue crack and improve fatigue life. So the third one is something you know, avoid sharp corners. And that's the stress concentration area. All right, that was about fatigue. It is rather quick, as I said, but it's got quicker for creep, because we're going to not focus on the mechanism and we're not going to focus on the theory and the equations, so on. Basically to let you know what is happening. So creep is something you probably never heard of from your previous education, because this is a very specific failure. It usually, as I told you, happens at high temperature and not kind of similar to any of previous loading. Previous loading always involves an increase in terms of stress or load. But creep is something like you apply a stress to your material. So this is time, look at it. And you just stay there. So you apply a certain stress to your material and you don't change, you don't increase it anymore, or you also don't decrease it anymore. You just hold there and make it constant to your material. What would happen? I mean, if your material is at very low temperature, extremely low temperature, nothing would happen. Yeah, so if you just look at this diagram, this is the strain, yeah, and this is time. You see, if you apply a stress, you will cause a certain deformation, and this is strain. If it is at low temperature, this strain just stay there, yeah, like that. But if the temperature is high, typically close to the 40% of the melting temperature or larger, yeah, pay attention, this is in Kelvin. It is different when you calculate with the Celsius. You will trigger the so-called creep. Yeah, it will not tell you the mechanism for this phenomenon, but I describe you the phenomenon. The phenomenon is your material is gonna get longer. So if we assume it's a tensile strength, and it will just increase. So first of all, it increases rapidly. So this is so-called the creep rate. If you just take the derivative epsilon over the d, you get the slope of it. And it goes very fast at the beginning, and then it slows down a little bit. This is the first stage is so-called primary stage. It enters to the secondary stage when the slope becomes more or less a constant. Yeah, the slope is, the curve is becoming linear. And this actually takes up the most time of your creep life. Yeah. And thirdly is the last stage is tertiary stage, and your kind of creep rate is getting accelerated again until you get this kind of fracture or rupture and so on. So you see, this is how creep happens. Yeah. You hold your strength, but your material is just getting longer and longer. Yeah, very weird to imagine, but it happens. The condition is you have to get high temperature. You see, the creep phenomena is highly correlated, first of all, with temperature, second of all, with the strength, and the strength that you're going to apply. Basically, you can already imagine, I'm not giving you any equation, but you can imagine if the strength is high, basically your creep life will be short, yeah, like this. So we're talking about the time. See, this is time. If your temperature is getting higher, it's very high, then your 20% of melting temperature, your creep life is also getting shorter. That's the point. So there's kind of equation, not the full equation, just partial equation to describe the second stage of the creep life. So the secondary stage, because that's a linear, that is easy to explain. You don't need to remember this equation, just here it tells you a little bit of quantitative correlation between the creep rate with respect to stress and also the temperature. Yeah, so you can get a basically feeling about it. All right, that was the creep. So as you see, it's getting faster and faster. And the final item is the corrosion. But before we go to corrosion, I would like to give you a quick, let's say, recap about what we learned for all the mechanically induced failure, because corrosion is not a mechanically induced failure. So first we talk about cleavage fracture. Let me change the color to make it a little bit better. So first we talk about cleavage fracture. So this is the typical stress strain diagram. Yeah, for cleavage fracture, it happens like this suddenly. And then we talk about ductile fracture. It can also be visualized by such a diagram. Yeah, stress strain, and then you have deformation, elasticity, plasticity, and finally fracture. And then we go to fatigue. Yeah, fatigue is something a little bit different. So we're not using epsilon anymore, we're using time, right? And here is either your stress or strain, and you're applying a load repeatedly, and go on and on. Yeah, until at a certain point you get fracture. And we record the time, which is the cycle number, and also the stress amplitude. And finally, we talk about, creep. Yeah, so this is time again, and this is only stress, and we're holding our stress and constantly, then the strain is going to be developing. So actually, if you imagine, try to correlate all this together. So this is also time. So strain is type of time. The strain is basically developing monotonically to your time. Yeah, if you just try to draw it, strain time diagram, it's looking like that. And here it's also somewhat similar. Yeah, and here is exactly like this, but here is different. So the strain time diagram is looking something like this. Yeah. So this will help you basically to correlate everything together and try to get the understanding about it. All right. The last item is about corrosion. So corrosion is something you probably know the best because you have learned it in a pretty systematic way from your high school, especially chemistry. And what is the definition about corrosion? So first, I probably didn't write it here, but you know the definition of corrosion of metals is basically your metals is losing their electrons, yeah, in oxidation environment. Yeah, then you're going to develop some oxides on the surface of your metal, and that is the so-called corrosion. So the key word is the metals are losing electrons, and in a way, they're also losing the material partially, very little. And that kind of ions that you develop by losing electrons will react with the oxidation environment, and finally you develop some oxides on your surface. So you can see this is the reactions, so oxidation reaction for the metals. So here I'm taking zinc as a typical example. And if it is in, let's say, acid kind of environment, you will have such a reduction reaction in the other side. If it's in acid solution or neutral, basically you're going to form water. Yeah, everybody knows about this. And the important part is not all the metals are going to develop in corrosion. It really depends on their standard electrode potential. Maybe you know this. Yeah. For example, if we take a kind of anode metal, platinum, yeah, on one side, and if you take other metals to, I need to find out where's this, I need to change the color. And if you just take your metals on the other side, if the potential of your metal is smaller than platinum, yeah, platinum, and they're basically gonna lose the electrons. And here you see your material is losing, because part of it becoming ions, and that is so-called corrosion. But you could also go opposite, right? You don't lose, but receive electrons, and they kind of metal ions are going back to your position and becoming metals. And this could also happen. And this is so-called electron deposition. And actually, this is one of the mechanisms you probably would fix things. For example, if something is really getting bad and losing the surface, and you try to use this to deposit some metals on it. All right. And this is the typical, let's say, standard EFM series. Basically, over here, you could find out which metal will lose ions, their electrons compared to the other one. And for example, here you see the zinc. Zinc is one of the pretty active one. And copper, gold, platinum, they're inner ones. All right. So we'll not talk about too much about that. And this is typical, a very important or interesting example or experiment. You probably have seen it in your kindergarten or primary school. Basically, you put a zinc kind of foils into a grapefruit, and you will see how the zinc is getting oxide. And you will also see there's some electricity generating because the electrons are moving basically from the zinc and to the other end. And why we're choosing usually a grapefruit, you could also go with other fruits, but the grapefruits really provide a pretty acid solution that makes it work. All right, so that was enough basically to give you a definition about corrosion and how it looks like. And once again, a few items to basically prevent or improve the corrosion property of your material. So the first one is related to material selection. So if you have to choose a material which is going through some acid situation, you first could choose those very anode ones, but they're also expensive actually. But the second one is more engineering relevant, which is you go with this so-called metals with passivate features, meaning that is why we're developing aluminum alloys and stainless steels. Maybe you don't know how the stainless steels could go against corrosion. Actually, it's pretty simple because these metals will form a thin layer with oxidation, and that kind of thin layer will basically frozen or kind of slows down the corrosion significantly. So that is why we could go with the corrosion behavior with the stainless steel. And the second point is lower the temperature. This is something about chemistry. If the application temperature is low, you will reduce the rate of oxidation and reduction, but sometimes you cannot decide that because that is related to your temperature. And the third is to apply some physical barriers, for example, like film, something not made by metal, like film or coatings. And the fourth one is add inhibitors. So this is also a way to reduce the reaction about oxidation and reduction, but more like chemically, not by lowering temperature. What is more important is the last one. This is a mechanism that is usually used for many steels. It is so-called cathodic or sacrificial protection. Maybe for many steel sheets, we're going to use the zinc layer to protect the steel from corrosion. But you don't know why. Zinc is not an anode material. Zinc cannot develop a film or layer to go against oxidation. Why we're using zinc? Actually, the reason is pretty simple, because zinc is active. Basically, zinc is going to sacrifice itself to donate its electrons to the environment and develop all these bad surface qualities to prevent the steel is doing their job in a proper way. And this could also apply to magnesium. And this is basically used to protect the steel pipes. The working principle is exactly the same. So now I think 5 ways to improve the corrosion property. And that is also the end of our last failure. So here I would like to give you a quick summary about what we learned for today. So we talked about ductile fracture behavior, and you know ductile fracture is different from damage. So damage is basically represented by voids, and the mechanism for ductile fracture is about void nucleation, growth, and coalescence. That's the ductile fracture part. And how do we quantify and describe and predict ductile damage? And this is how the ductile damage mechanics models are developed and how to use them. And you will experience that during your exercise, and at least part of it. And but not all the ductile materials will always fractured in a ductile way. You know, ductile materials could also go through the ductile to brittle transition, so controlled by some features you learned already, and you will also learn an important test to basically describe the ductile to brittle transition. Actually, I would have one question for you. You know, why we're not using the tensile test to do this? Why we have to invent a different test? Yeah, you could think about it. And then we learned about fatigue. So you learned how the fatigue is defined and how we're gonna kind of describe it using a map. And we also learned the creep, same thing. And you also learned about corrosion. So what is corrosion and how could we improve and avoid corrosion? I think that would be all for today's lecture. And I think we still have a few minutes left. I'm gonna use this few minutes to collect some feedback and trigger your thinking about midterm review. So we're not having a midterm exam because the period basically too short to do any exam. Instead, we're promoting a midterm review. The idea is that we're gonna collect some feedback from you. Yeah, I wanna know how you're doing with this course. And because this is exactly the half of the course and you are learning as the main, let's say, participants. If there's something that we feel very good, we're going to keep up there. If there's something we feel we need to make a change, we're going to do that as well. Basically, that is a chance for you to reflect on yourself, because the ultimate goal for us is to make you understand this lecture and acquire the necessary knowledge, not just, you know, making it difficult that you cannot or pass the exam. That is the opposite. So to begin with, I will show you some or refresh your mind about how this course is constructed and how you basically get the final grades. So I think everybody knows about that. You come to the lecture, you come to the exercise. The reason why you are coming here and you are getting points actually is pretty easy. There are twofold. The reason, because some people ask, why don't we just make it online and you just learn it anytime you want? Yeah, this is the first idea is we always need a community. You know, you need a community to learn better, and I need a community to teach better. So you're coming here also to help me to teach better, because if I'm just speaking alone, I'm less motivated. And when you're here, when I could interact with you, then I could give you better knowledge. So you're earning points for helping me to teach you better. Yeah. The second point is these are really easy points for you to learn, for you to earn. So you will get something at least by the least effort you could do. Yeah. And so these are the 10 points for participation. Don't remember there's 1 point for forum discussion. So you can get a point if you just post something. You ask a question, you answer somebody else's question. You'll get that. And now I'm wondering why the second slide doesn't show. Okay. Then you have the majority of the points coming from the weekly tasks. Yeah. So you know about that. 6 weeks and we have 40 and 50 points coming from exam. And this is already 100 and the last 10 points are extra. So these are really reserved for you as bonus points to basically improve your score. So if you don't make a very good score with 100 points, so the extra points will make you better to reach a higher score. Yeah, but you cannot only do this, right? To be able to receive this point, you need to finish your tasks. The majority of your tasks, you need to take the exam. Yeah. So you cannot just by participating and doing some tasks and doing some extra activities, you want to pass the course. That is not possible. So the exam is the prerequisite for you to get this extra points. Okay. I hope you got it. And finally, we're going to use extra, let's say maximum 5 minutes to collect some quick feedback for you. But I'm not sure if this is running. If you could try it and basically go to the medi.com, I will do something actually for you, because I think I could copy this link and post it in chat. That will help you to do a voting easier. And the first kind of feedback I would collect is, how many hours did you spend on studying and working on assignments? So basically this is collecting how many hours you are doing individually for this course per week. If you could just try to click the link and find the 3 categories. If you are just spending less than 15 hours, or if you are spending between 15 and 25 hours per week, or you are spending even more than 25 hours per week for the course, that would be interesting for me to see how you develop.
The first question for me, at least, is not that. It's how do you feel like the course, and use adjectives to describe. I don't know if I missed one.
Oh, that's important. Oh, thank you. I have to switch the slides from another platform. Can you try again? Can you refresh?
Yeah.
Okay, refreshing works.
Is it working?
Yeah.
Excellent. So thanks for that feedback. See, feedback is really important. Oh, I'm already showing the answer right now, right? It's real time. So I see some people are coming. Excellent. 13, 14. Cool. Good. This is some result I would like to see the most, because you know this kind of hour, let's say 20 hours per week, is an ideal hour, for everybody to devote to the course. That will make about 140 hours per this period for the course. It's always something plus minus 5 hours. So I don't want to see too many pluses. So 20 to 25 or even higher, that is not good. And there's some ones spending less. That is good. All right. So that is awesome. And now we can move to the second one. I'm gonna activate it now. Some people already wrote a few words over there. So now if you don't need to switch the code. If you just refresh, give me 1 second. I think I need to go there, and yeah. And now if you just refresh the link, you'll basically be able to see another question. Here you could use 3 adjectives to describe the course. So very short, don't put too much energy on it. I just want to see some, typical impression, how you feel like about the course. Cool. So some answers are there. Confusing, time-consuming, exciting, difficult, interesting, hard, 15. Okay, so that was from the previous time. All right, so keep running. I would like to see more. But if you think 3 adjectives is not enough, and it's certainly not enough, that's why in your assignment, probably you have already seen, we are giving you 1 task to reflect. So this task is basically the reflection of this course, how you learn it, how could you improve from your side to learn it better, and what kind of suggestions you would like to give also for the course to better suit you. Yeah, you can start here from your individual point of view, and I would be interested to see how you reflect your study. Basically, it's let's say a learning kind of diary on the learning law that you would like to do in the middle of the course. All right, so thank you for those who voted with this extra time, and I think we could stop here. So, and I would be interested to see your more detailed feedback. So lastly is about some announcements. You see we have same thing basically. What is important is you have this 2 chapters to read if you want to refer to textbook 8 and 17. More importantly is this week, I've already mentioned a few times, you're going to learn FEM, and you will learn with Wenqi, and you will learn individually also, or in your group, about ductile fracture modeling. But before that, you need to prepare your environment. So environment is done with FEM, it's Abacus. So this is typical for the preparation of the course. And you can download this from the student version to install on your own PC, or you could also find it from the virtual environment, as you are already pretty familiar with. So both ways will work. Now, here is a detailed installation description prepared by Wenqi for to do it. All right, I think that's all for today. So we could stop right here. So thank you for the extra moments and also the providing of feedback. And if you have questions, you could ask. Otherwise, I would wish you a good day for today and the rest of the week.
Thank you. Bye.
Thank you, bye.
Bye-bye. Bye-bye. Cool. 文琪荣肥，拜拜。